The first detailed images arrived quietly, without fanfare, but they immediately unsettled expectations. When astronomers turned their most powerful instruments toward the interstellar object known as 3I-ATLAS, they expected something familiar. A growing haze, a faint cloud of gas, a subtle tail forming as solar heat awakened volatile ice. Instead, they saw none of it. Against the dense background of stars, the object appeared as a sharp, compact point of light. Clean, defined, unchanged. Even as it moved deeper into the inner solar system, the surface showed no halo, no dust, no sign of activity. Hubble, capable of detecting the faintest traces of gas and debris, found nothing at all. Image after image confirmed the same result. Whatever 3I-ATLAS was, it was not behaving like a typical comet. This visual stillness became the baseline. For months, scientists monitored the object as it approached the sun, expecting the inevitable transformation. In comet science, heating is not optional. Bodies of this size and composition should begin shedding material well before perihelion. Jets of vapor usually erupt, dragging dust into space and building an expanding coma visible across wavelengths. But Atlas remained stubbornly unchanged. The summer data locked in a reference point, a snapshot of normality that would later make every deviation impossible to ignore. The object's refusal to react to solar heating was not dramatic. It was methodical, and that made it far more unsettling. While images showed calm, the numbers told a very different story. Modern astrometry tracks celestial motion with extraordinary precision, and by early November, something was clearly wrong. Atlas was drifting away from its predicted orbit. The deviation was small in angular terms, just a few arcseconds, but at its distance, that translated into a displacement of tens of thousands of kilometers in barely a month. This was not observational noise. It was a persistent, directional shift. Calculations revealed a non-gravitational acceleration acting on the object, roughly 0.02 millimeters per second squared. That may sound insignificant, but over time, it is enough to dramatically reshape a trajectory. Gravity alone could not explain it. The force appeared continuous, not impulsive. Part of it pushed radially, part laterally, exactly the kind of signature expected from sustained thrust. In comets, that thrust usually comes from outgassing, material erupting from the surface and acting like natural rocket exhaust. But there was a problem. No coma, no tail, no dust, no gas. The sky showed nothing that could account for the push being measured so clearly in the data. The object was being nudged steadily and measurably, without leaving any visible trace of how. On October 30th, 2025, Atlas reached perihelion, its closest approach to the sun. If there was ever a moment for activity to reveal itself, this was it. Yet nothing changed. The object passed through peak heating and continued outward, visually identical to how it had looked months earlier. This set the stage for the most critical observation window yet. On December 19, 2025, Atlas would make its closest approach to Earth, still safely distant, but close enough for unprecedented scrutiny. Space telescopes and ground observatories around the world scheduled coordinated campaigns, preparing to capture every possible signal. After that, the object would head toward Jupiter, experiencing one final gravitational interaction before leaving the solar system entirely. There was no danger to Earth or any planet. The stakes were not safety, but understanding. These dates formed a natural experiment, a sequence of checkpoints that could confirm or dismantle competing explanations. Either Atlas would finally behave like a comet, or it would force scientists to confront a far more uncomfortable possibility. The physics behind the mystery is unforgiving. To accelerate a solid body roughly 6 kilometers wide by the amount observed, an enormous amount of momentum must be transferred. Estimates place the object's mass at tens of billions of tons. To generate the measured acceleration through outgassing, Atlas would need to lose billions of tons of material in a very short time. That kind of mass loss is not subtle. It produces a brilliant coma, a dramatic increase in brightness, and long dust tails visible even through modest telescopes. Yet every instrument sensitive enough to detect such effects reported silence. This is not an abstract disagreement between models. It is a direct contradiction. The math demands visible consequences. The sky refuses to show them. If conventional comet physics applies, then the evidence must appear during the next observation window. If it does not, the explanation fails a basic test of consistency. In response, the astronomical community mobilized. From late 2025 into early 2026, ATLAS became one of the most closely monitored objects in the sky. The James Webb Space Telescope allocated infrared time to search for even the faintest thermal signatures of escaping gas. Hubble continued high-resolution imaging, watching for any structural change. Ground-based observatories rotated through photometry, spectroscopy, and polarimetry, each technique designed to catch a different kind of signal. If water vapor, carbon monoxide, or exotic volatiles were present, they would leave unmistakable fingerprints in the spectra. If dust grains were scattering sunlight, polarization measurements would reveal them. Behind the scenes, teams calibrated their instruments to extreme sensitivity. Detection thresholds were set conservatively to avoid ambiguity. The goal was not interpretation, but clarity. Either something would show up or it would not. Both outcomes were scientifically valuable. Then came another complication. Photometric analysis revealed that ATLAS's brightness increased sharply as it approached the sun, far more steeply than expected. Instead of following the gentle curve typical of comets, the light curve rose with an unusually aggressive slope. This kind of behavior is rare, and when it does occur, it is almost always accompanied by explosive outgassing. Yet once again, the images showed nothing. No expanding cloud, no dust plume, just a brighter point of light. Color measurements deepened the puzzle. Near perihelion, ATLAS shifted toward the blue end of the spectrum. Dust-rich comets tend to appear redder as larger grains scatter longer wavelengths. A blue shift suggests either hot gas emissions or an unusual surface interaction with sunlight. But neither explanation fits comfortably with the absence of a coma. Multiple instruments confirmed the result, ruling out calibration errors. The color change was real. By this point, anomalies were stacking up. The object's trajectory was unusually aligned with the plane of the solar system, statistically unlikely for an interstellar visitor. Reports suggested directional features that did not align with standard solar heating models. Its size was large compared to most known interstellar objects, and its velocity exceeded expectations from ejection simulations. Chemical signatures hinted at unusual elemental ratios, including elevated nickel relative to iron and a striking lack of water. Polarization data did not match known comet dust profiles. Even to rival direction coincided, intriguingly, with regions of past anomalous radio signals. Individually, each oddity might be dismissed. Together, they formed a pattern that resisted easy explanation. Some scientists argue that nature is simply more inventive than our models. Others insist that extraordinary claims require extraordinary evidence. One prominent voice in the debate emphasizes process over conclusion. The method is simple. List the anomalies. Test each one. Define clear criteria that would confirm or falsify conventional explanations. If a bright coma appears at the predicted brightness and scale, the case is closed. If gas emissions reach the necessary production rates, the mystery dissolves. But if those signatures remain absent, then the data demand a broader conversation. This is not about leaping to sensational conclusions. It is about refusing to ignore contradictions. Science advances by confronting what does not fit. ATLAS offers a rare opportunity because the test is clean and time-limited. The object will either reveal itself as a